Okay, we're going to talk about writing our own data types using the Haskell data type mechanism. So let's start with a simple binary tree. Say the data tree, I'm going to call my data type tree. It's going to be parameterized by the type of things that it can hold. It can hold any type of thing. A stands as a variable, a type variable. And I'm going to have a leaf which contains nothing, or it's going to be a fork of that has an A in it and has a tree of type A and a tree of type A. Now, if we're going to use this, I need to derive, at least show that I'll derive EQ too, so we can do a little bit more. So we can derive EQ and show. So what does that mean? Haskell is figuring out, okay, here's a data type. I know how to show this. When you type in leaf, I'll show you leaf. When you type in a fork constructor with an argument and two subtrees, as long as A is showable, I'll be able to show you the word fork followed by whatever A is, followed by the left subtree, and followed by the right subtree. Let's start a terminal. And I'll start the interpreter and I'll load tree. Okay, so what is the type of leaf? Leaf is a tree. So I can just type leaf and it returns to me leaf, the evaluator. If I say, what's the type of fork? Fork is a curried function that wants 1, 2, 3 arguments, something of type A, a tree of type A, and another tree of type A, and it returns. It's the way of constructing trees of type A. So fork of, let's say, 7, leaf is a tree. And how does it get displayed back to us? It gets displayed back as fork 7, leaf. So I think some students have a little difficulty with this idea that this thing is a tree, and it's how it's being displayed to you, and it's how you're writing it down. You write it down by applying the constructor name fork to, in this case, a number, and then leaf. So I can build another tree. I could say, oh, okay, I don't want this one to be a leaf. I want this to be a fork with, I don't know, 4 in it. And 2 leaves. And that's a tree. And I could say, oh, wait a minute, I want to grow this over here. Like this. Okay. And there. So these are trees, but it's a little tedious to type all this in. So let's build a little function. We'll call it from list. And it'll take a list of things of type A and return a tree of type A. And so from list is by recursion on the structure of the list input. And so if the list is empty, we're just going to return a leaf. And if the list is not empty, I could write X colon X's, but I don't want to select the root from the front of the list. I want to select the root from the middle of the list and kind of build the tree from the middle out. So I know that if it didn't match the empty list, if it gets here, then I know that this thing here is a non-empty list. And what do I want to return? I want to return a fork. And I'll say, okay, I'm going to pull X out of the middle. And then I'm going to have a T1 and a T2. Now, how do I get them? Well, I am going to dog needs to be let out. I'm going to get a pair. I'm going to split the list. So on the right-hand side over here, I'm going to say split at, and I want to split it roughly in half. So I'm going to say it's the length of x's, and then integer division is div 2. And which list am I going to split? I'm going to split x's. And what am I going to call the rest? Well, I want to call, let's see, I want to have y's is going to turn into t1. And then I've already given the name x. And then I'm going to have, let's say, z's. So this x, I'm pulling out of the middle of the list. And, you would have to play around a little bit with what does split at do with, like a 0. So if the length of the list was 1 divided by 2 is 0. And so you'd get a list like that. Split at. Well, if the length of the list was 2 divided by 2 is 1. So then I have 1, 2, and so then it's evenly split. But now, if the length of the list is 3, it's still 3 divided by 2 is still 1 in integer, and so you get like this. And x should be splitting at 2 for a list of length 4, and so on. So there's always an element that's on the head of the second list with this equation here. So that's going to be my x. And then I've got stuff on the left and stuff on the right. And so now I can say, okay, I want T1 to be the recursive call from list of i's, and T2 can be the recursive call from list z's. Now, I almost don't like this as much as maybe replacing this up here. Copy or cut and replace that with paste. I almost like putting the recursive call up here a little bit. It just makes the program shorter. It's not like the recursive call is so big. So, I mean, it's just a matter of style. But okay, so now my program is a little bit shorter, and the recursive calls appear on the same line up there. Okay, so let's save this. Let's load it. What did I do wrong? I quote messed up. Outside, the back quotes outside of that. So save that, load that. Okay, so now I can say, from list, and I can build a fairly large list. I can turn a list into a reasonably sort of more or less balanced tree. Let's see, what is the height? Let's write a height function. Height of a leaf is going to be 0. The height of a fork, I don't even care what's stored in the tree. T1, T2 is going to be equal to T1 plus the max of the height of T1 and the height of T2. All right. Save that. Let's reload that. So now we could do something like, we could do that. We could say the height of it is 4. And so that doesn't count leaves on the bottom. So that's pretty good. What is the height of a prom list? 16 elements in it is 5. So it's not perfectly balanced, but it's reasonably good representation of a compact tree. Okay, so now in the comments on the homework, some people were interested in functors or they found them confusing. And basically all a functor is a it's a type class. And in Haskell, a type class is not really the same thing as a class in an object-oriented language. A type class is a collection of data types that share some property can be included together in a type class. And so any data type that has some kind of reasonable notion of mapping, applying a function to the elements in the data type is something that can be a functor. So we make it an instance of functor. We're going to make tree an instance of functor. And to do that, we have to define fmap for trees. And so fmap takes a function and then a tree, and it returns, in the leaf case, a leaf. An fmap of f applied to a fork, whoops, with, I don't know, an x and a t1 and a t2 is going to be equal to fork of apply f to x, and then recursively call fmap on T1 and recursively call fmap on T2. So that's a mapping function for trees. Let's see what we get over here. Load the trees. Okay, so now I could do something like, oh, this might be interesting. What about map height? Is that gonna work? No, that's not going to work because the function f is from the type of thing stored in the tree, not the node itself. So we could say show. So for example, I can apply the show function, which works on numbers. And instead of having the number 5, for example, here, I have the string 5. So this is a function that, I've applied this to every single one. Let's try, let's add, whatever, times 2, multiply every element in the tree times 2. Okay, here they are. They're, 18, 10. They're all even numbers. We've multiplied every number by 2. So that's how we can make trees an instance of the functor type class. What about folds? There's another type class called fold, and I've included data.foldable. Functors are so common, it comes in from the prelude. Um, Foldable types are less common, but trees are foldable. You can say instance foldable tree where. And now to define a fold, you got to either define a fold R or a fold map function. And so I'll do the fold R. And, like up here for fmap, you had to define, there's only one thing you have to define is fmap. Now in foldable, you got to either define a fold map or a fold R. And then everything else is derived for you, all these other functions. So let's do a fold R, and I'll call the function and the operator that I'm applying F, and I'm going to have a 0 element for the operator, a right identity because we're folding to the right. And if it's a leaf, we just return. Well, and in fact, we're going to end up using this more like an accumulator. So I'll say ACC. It's an accumulator, but in the base case, it's going to be an identity element. So fold R F ACC of a fork with X and T1 and T2 in it. Now, this is tricky, and let's see if I can remember what it is. I want to take F. No, I'm going to build it inside. Now my dog wants to come in. Hang on. So let's see. This one is a little bit tricky. It's I'm going to take, and I'm going to use ACC like an accumulator. So I'm going to do a fold R and F. And what am I going to put in here? I'm going to put in here F applied to X. And now what do I need to do? I want to have this be right associative. So I want to build up towards T2. So I'm going to say fold R F ACC, whoops, T2. And now this fold R here will have accumulated X. Everything on the right-hand side will have been built up, and the X will be applied last. F of X will be applied to this whole thing, and then we'll say T1. So go the other, you now do the left branch. And if I save that, hopefully I got that right. Let's see. Okay, and so now I could do like a fold R. Okay, let's see. I don't know. Maybe I should create a few versions here. I should say like I don't know. Let test one equals at least, and I have one that I don't need to constantly type the question in over and over. Well, what is it doing? Oh, I don't say let there. In the interpreter, I say let. Okay, T1 is going to be that thing. Now I can load this. And so T1 is now bound to that test case. So now I can say, like, fold R, and I'm going to fold R with a plus and 0 and T1. And get back 136. Now, how can we know that that's right? Well, I don't know. We could do a fold R on the from list on with plus 0 on the list 1 to 16, and it says 136. So assuming that our function that we wrote up here from list to build a tree from a list has the same elements in it as the list it was built from, these two things give back the same answer. Now you might wonder, how the heck did this happen down here? Here I'm running foldr and it's being applied to a tree, and here I'm using foldr and it's applied to a list. And what's really happening when you create an instance of a data type, of a type being in a type class, what you're doing is you're adding information to that the compiler uses to figure out which foldr function do I want to use. Oh, the argument here is a list. Okay, so I'm using the foldr that's defined for lists. Oh, the argument here is a tree. Okay, I'm going to use the foldr from a tree. And so this is called ad hoc polymorphism. Like, you just kind of like make it up by adding new instances, which is different from the polymorphism that we get when we, type in a very general function, like, I don't know, height of a tree, for example. What's the type of height? Height, as long as it's basically saying it returns a number, and the tree can be anything. T1 doesn't have any constraints on it. And so you can take a tree of any kind of thing, T1, and, functions or whatever, and return, you're going to return a number that's ordered as well. And that's because max function is requiring the ordering on there. Okay, so that's a little bit more about writing your own data types. We'll do another one on kind of building a little programming language next.